All right. Okay, so welcome everyone. Before the talk, I would like to briefly introduce our seminar series and explain our reasons for organizing this series. So, as a group of students, mostly undergraduates from Middle East Technical University in Turkey, we independently prepared a consistent series of seminars on theoretical physics for the upcoming months. And I am pleased to see you all of you here right now, and I hope that you will keep coming to our future events. So in this seminar series, our primary motivation is to hear about recent developments in the theoretical physics literature firsthand, as well as to interact with the researchers behind these advancements. And beyond this point, the series is also an act of criticism by us to our department, as we strongly feel that we were devoid of such seminars during our years of undergraduates here. And such meetings being the essential way of communicating original ideas, we found it incumbent to take the initiative and start this series as aspiring theoretical physicists. And we hope that our act leads to a much richer and interactive scientific environment, which we know we all deserve. So, on a more somber note, I would like to mention the recent and untimely passing of Umut Gürsoy from Utrecht University. He was certainly one of the respected physicists coming out of Turkey and an important figure for us young people. And it's very sad that we will not have the pleasure of meeting him personally. So we, as the organizers, wanted to commemorate him with the debut of our series upon hearing the sad news of his passing. So that's all I wanted to say about our series. Thanks again for coming. Coming back to our talk, we have a very distinguished guest in our first seminar, Zohar Komargodski. So, Zohar is a professor of theoretical physics from the Simon Center for Geometry and Physics at Stony Brook University, and he will present his latest work on the series of exciting developments concerning ordered phases at high temperatures. So, Zohar, thank you very much for accepting our invitation. It's a great pleasure and excitement to see you, have you here. So you can start your talk.
Okay, thank you very much. Actually, this topic of finite temperature, the behavior at finite temperature of many body systems and quantum field theory was a big field of expertise of Professor Gursoy. So it's I think a timely topic and a very untimely passing. So I'll talk about my series of my little obsession over the last couple of years with trying to understand the Gibbs ensemble or the Boltzmann ensemble in many body systems. It started from some work with Sumya Deep, Noam, Changha, Eliezer, and Misha. And then there was some open problem that took me a lot of years to solve. And eventually, with Fyodor, we were able to crack it finally, just recently. And this led to another paper with Yiqiu Huang, Xiaogang Huang, Andy Lucas, and Fyodor. This is from Colorado and Stony Brook. And I think this is the most relevant paper for today. That's what I'm gonna talk about mostly. And of course, at any point, please stop me with comments, questions, and any ideas. So, just as a piece of history or background, of course, many Hamiltonians exhibit symmetry breaking. That means that at low temperatures, some internal order parameter points in the same direction throughout the sample. In real life, we see that by having large regions where let's say, some arrow, like a magnetic order parameter, points in the exact same direction. And it's kind of so there is this phenomenon of symmetry breaking. It happens in quantum chromodynamics. It's very important for pion physics. It happens in superfluids, in magnets, many systems. And then there is also a more exotic type of order, which is called topological order, but I won't really get to it today. But it's not very dissimilar from what I'm talking about. Now, another thing that we usually learn in school is that if we crank up the temperature, the order should disappear. So the symmetries are restored, meaning that there will not be domains where the arrow points, some internal arrow points in the same direction, because thermal fluctuations will just disorder the arrow everywhere. And that's a, let's say, folklore theorem that we learn about in high school. So let's try to understand what is the mathematical justification for this widespread expectation. So first of all, one reason is that when we look at materials in nature, this is just a phase diagram that I stole from a paper of Bitko and coworkers. If you look at any phase diagram of any magnet, this is a magnetic system uh, as a function of temperature. So temperature is the vertical axis and the horizontal axis is a magnetic field. So there is some region where you get magnetic order. So there are large regions in space where the spins point in the same direction, but the yellow region is just thermal fluctuations. So the arrows are completely disordered. And very importantly, you see that this black line is bending to the left. There is a very important point here where the black line touches the zero temperature axis, which is a phase transition. It's a quantum critical point, or in high energy physics language, it's a conformal field theory. And at that point, there is a black line that comes out, and the black line bends to the ferromagnetic side. So the ferromagnetic side is capped by the black line, and you get thermal disorder at very high temperatures. And if you look at phase diagrams across many materials, it always looks like that. It looks like the ordered phase disappears at high temperature. So that's one reason that we just see it in experiment and in many, many simulations. Another reason is more theoretical, is that what we minimize at finite temperature is the energy minus the entropy times the temperature. It's because we have to take into account the number of states at a given energy when we minimize the partition function. So if you put very high temperatures, you should therefore maximize the entropy. And then what is entropy? Entropy is disorder. Maximizing the entropy means that we're increasing disorder. So therefore, it would seem to make no sense to have an ordered arrow in the sample because that's clearly a very low entropy state. Entropy tells you how much information is encoded in the state. If the arrow is ordered everywhere, then there is almost no information. But in a disordered system, there is a lot of information because you need the full microscopic configuration to specify the system. So therefore, we're told that high entropy are disordered states. So this is a theoretical reason, and the previous was just an experimental reason that we just see that ordered phases disappear at high temperatures. And another reason that we expect that symmetries are restored at high temperature comes from the ADS-CFT correspondence. Of course, this is not the main reason. This whole discussion was already known in the 60s, but the ADS-CFT correspondence gives you another point of view on that, because in ADS-CFT, high temperature states are dual to black holes. And the statement that there is no order at high temperature is dual to the fact that black holes have no hair, which is a famous theorem, probably by Penrose Hawking or some of these people. And indeed, there is a lot of work in the ADS-CFT correspondence about the question of whether there is hair in large black holes. A lot of work mainly by Alex Bushel from recently, and they don't seem to find hair. So for all these reasons, it's widely expected that anytime you have a phase diagram like that, there is an ordered phase, the black line just goes to the left, so to speak. However, we can ask a question, it's a theoretical question at this moment. Can it be that there is some phase transition at zero temperature from which the black line bends to the other side? That would seem crazy because the ordered phase would dominate at high temperatures and the disordered phase would be capped. Okay, so this is a theoretical question you can ask about classical or quantum systems. Is the motivation clear? Okay, so far I gave you some vague arguments for why this should be impossible. Now let me give you more concrete arguments why it should be impossible. So there are theorems. There are theorems that I'll now explain what they say. These theorems are summarized in a very nice book by Barry Simon about classical models and quantum models. What do the theorems say? The theorems are called the uniqueness of the Gibbs ensemble. So the theorems say that at high enough temperatures, at separated points, which are very widely separated, any correlator decomposes to products of one-point functions. This is cluster decomposition. Sometimes we say this is cluster decomposition. This in particular implies, this is not true, by the way, at low temperatures. Not. It's only at high temperatures. There is no there is no decomposition in this sense at low temperatures. So this in particular implies that the system cannot be ordered because the spin at point X and the spin at point Y cannot be correlated according to this equation. Their statistical distribution is a product of the single particle distributions, and therefore they cannot be correlated. Okay? So under some assumptions, it's actually possible to prove that starting from some temperature, there cannot be correlations in the system. This is explained in this book, and it sometimes goes by this theorem goes by the name of the uniqueness of the Gibbs state. And I mean, as a physicist, it's very easy to prove this theorem in an expansion around infinite temperature, but mathematicians were able to actually prove that this expansion converges, and it's true starting from some finite temperature. Okay, so this is actually a non-trivial result. Another name for this kind of theorem is heat death of entanglement, because the absence of correlation turns out that it also implies the absence of entanglement. This was proven more recently by Clich, Gogolin, Costoriano, Riera, and Isert. And so the message here is that high temperatures, there is no entanglement, there is no correlations, there is no order. And this can be proven under some assumptions. And this is very nice. Now, however, it should be said that there are some examples where something a little weird happens. These examples are still not a contradiction to these theorems. So one example where something a little weird happens is in some particular salt that you can actually buy on Amazon. And this salt has a weird feature that there is a small range of temperatures where it's a little bit more ordered than at lower temperatures. So usually for crystals, when you heat them up, they become a little bit less symmetric and eventually they melt. That's what happens in ice, for instance. But this particular crystal becomes a little more ordered in a small domain of temperatures than at lower temperatures. Something similar happens in helium-3, which is a superfluid at low temperatures, but there is a small window when it becomes a solid all of a sudden. So it goes from liquid to solid for a very small range of temperatures. This is called the Pomeranchuk effect. And a similar thing happens in graphene. This was demonstrated recently. These are not by any means violations of these theorems, because these are just small ranges of temperature where something a little weird happens, but it's telling that maybe there is something. Maybe we should understand how is this possible. Maybe we should try to understand if it's generalizable to maybe infinite temperature. So when you dig into this theorems about uniqueness of the Gibbs state, it turns out that they have two assumptions. All these proofs about the uniqueness of the Gibbs state have two assumptions. And basically, these two assumptions are never true. So that's what I'm going to tell you. First of all, they assume that the uniform distribution over the space of states exists. So let me just unpack what I mean. So when people tell you in high school that there is a uniform distribution over, like, let's say, rolling a dice, that makes sense. It means that every outcome has 1/6 probability. But when people say that there is a uniform distribution over the integers, that makes no sense. All right? There is no such thing as a uniform distribution over the integers. It doesn't have well-defined moments. It doesn't converge. Similarly, if the space of states is infinite, there is no such thing as a uniform distribution over the space of states. In quantum field theory, the space of states is also always infinite, so there is no such thing as the uniform distribution over the space of states. In lattice models, sometimes the space of states is infinite too. I'll show you examples. And then there is no uniform distribution over it. Another assumption, which I will not discuss today, is that the space of states is actually a direct product. So the states are just made out of local degrees of freedom that sit at different points in space, and the full space of states is a direct product. This is never true in quantum field theory, basically. It is sometimes true on the lattice, and it's sometimes not true on the lattice. So in some lattice models, such as spin ice, it's not true. In some lattice models, such as Ising, it is true. So you have to go case by case. Are there any questions so far about the setup and assumptions?
Can I ask a question about the first
Sure.
condition? So you
Yes.
said that in quantum field theory, the space of state is always infinite dimensional. Can we say that topological quantum field theory is a exception to that?
Yeah, in topological quantum field theory, the unit distribution does make sense.
Yeah. Okay.
Yeah, I should maybe have said that in topological theory, there is such a distribution. But in topological field theory, there is no dependence on temperature anyway.
Okay. Yeah.
Any other questions? Okay, so let me continue.
Sorry, you said that there's no cluster decomposition. So cluster decomposition is a principle of quantum field theory. So you said that it doesn't hold at
Well, it's a principle until it's not a principle. By the way, it's familiar voice. Who is this?
this is Alessandro Tomasello.
Yes. Good.
Sorry, I didn't introduce myself.
Uh, uh, I mean, this is okay. So when a system breaks a symmetry spontaneously, the order parameter is correlated across very long distances. And strictly speaking, there is no cluster decomposition.
Uh,
You have to assume a unique vacuum for cluster decomposition,
I
a
see.
unique non-degenerate vacuum. And that can be proven to be true starting from some temperature, but not at low temperatures. At low temperatures, you might have some large correlation, which are of order 1 between order parameters.
But when
Let's
people,
say you take quantum field theory in a huge box
yeah,
with and you assume that the quantum field theory breaks the Z2 symmetry spontaneously, then cluster decomposition would not hold because the one-point functions vanish, because the one-point functions just are like they have to vanish by the fact that they carry Z2 charge, but the two-point function would be of order 1 because there is symmetry breaking.
mhm. But so when people elevate them to even so they're part of the Whiteman axons or something. That's
I think people assume various things about the vacuum, like that it's unique or there is no symmetry breaking,
okay,
something like that.
okay, okay. One more
Usually in
example.
the context of algebraic quantum field theory, it's assumed that there is a unique non-degenerate vacuum at infinite
Yeah,
volume.
yeah, yeah, yeah.
And in that setup, those axioms make sense.
Okay, thank you.
So I have a question also.
Mhm.
Does the enhancement of the symmetry at high temperatures mean that there should also be a symmetry between high and low temperatures, like Kramer-Vannier duality maybe? So we expect to see more symmetries like Kramer-Vannier duality at more theories, maybe?
I don't see that. All I'm saying here is that the symmetries are restored, not that there is more symmetries, just that they are restored in the vacuum. I'm not saying there are more symmetries at high temperatures. I'm saying that the symmetries are unbroken at high temperatures. They're just in a different, they're realized linearly versus non-linearly on the local fields.
Okay, thank you.
I will not touch Kramer's Vanier. It's kind of irrelevant for today's discussion.
Okay.
In the paper, you'll see there is a whole section about Kramer's Vanier, but it's actually kind of irrelevant for the discussion. Okay. So I'm gonna try to answer these questions today. First of all, these assumptions are kind of never true in quantum field theory. They can also be violated on the lattice. And today we'll answer 3 questions. Does large entropy really mean that the system is disordered? That's something that we're always being told, that large entropy means disorder. The second question we will answer today, are there local lattice models which order at high temperature? rather than disorder. And finally, we'll talk about formal field theory or quantum field theory, and we'll discuss whether quantum field theories can break a global symmetry at high temperatures. Okay. Maybe just because there are some big experts in the audience, I'll say that I'm only discussing this particular ensemble, which is called the Gibbs ensemble. If you add additional chemical potentials or various phases, there is no theory. Mathematicians have not proven anything, and pretty much anything can happen. I'm just talking about the ordinary thermal ensemble. Okay, so I'll start from the simplest possible thing, which is classical statistical mechanics in 2 dimensions. You come up with some crazy Hamiltonian. You say that the probability for any microstate is just the Boltzmann weight, and you have to calculate the denominator to be able to actually evaluate probabilities, which is a big pain. And that's why people do Monte Carlo simulations, by the way, because calculating the denominator is very difficult. And the partition function, which is the denominator, is just the sum over all the possible microstates. That also defines the free energy of the system. Okay, so this is the setup. And now I'm gonna show you a model that does something crazy. Maybe you have never seen something like that before. Maybe you did, I don't know. So our setup is just a square lattice. I'll just take it to be a finite lattice. And then we take the large volume limit at the very end. And what are the degrees of freedom? It's kind of like an Ising model, but it's a very little bit, a tad more complicated. So the Hamiltonian has 2 terms. So what are the degrees of freedom before we get to the Hamiltonian? On each plaquette, you put an integer, a positive integer, 0, 1, 2, and you think about it as the number of bosons. So this setup is called lattice gas. So on every plaquette, there might be 7 particles, 8 particles, 2 particles, and they're bosons. So you can have any number of particles on every plaquette. And you choose some energy functional for these particles. So first of all, you just pay some fixed price, which we call 1, to put a particle on a plaquette. Doesn't matter how many particles already exist on that plaquette. Every additional particle costs energy 1. If that was the whole story, the second term, then it would be, of course, an easily, trivially solvable system because the sites don't talk to each other. The plaquettes don't even talk to each other. But then you put an interaction among the plaquettes, which is repulsive. This symbol means nearest neighbor interactions. So this plaquette talks to this one, and it talks to this one, and this one, and this one, not the diagonals, just the ones that are connected by an edge. And you say that there is a repulsion that goes like the square number of particles. Okay? Now this power 2, I'll say for the interested people in the audience, it doesn't have to be 2, it could be 1.5. The power of the repulsion could be 1.1. We don't know what happens if you replace the 2 by 1. So if the repulsion is linear in each of the numbers on each site, on each plaquette, we don't know what happens. I'm actually spending a lot of time trying to work it out. It's highly non-trivial. But the one where the power is the second power of the number of particles is kind of solvable. You can understand what's going on. Is the setup clear? This is very important. Are the definitions clear? Okay. So then you simulate this model. It's not a solvable model. You can just put it to the computer and simulate it. You just have to do a Monte Carlo simulation for the partition function, calculate the probabilities, and then do a Markov chain that tells you what's a typical configuration. And what you find is that at low temperatures, it's like a liquid. I'll tell you intuitively why all of this comes out soon. So some particles appear on some plaquettes. There is no particular order. You might look at it, you can see that it's just like a random collection of particles on various random plaquettes. And there are actually not that many particles on the lattice. And then you go to high temperature and you get a checkerboard. You see a very clear pattern, which is a checkerboard. So particles occupy plaquettes only on one sublattice, not on the other sublattice. And that continues to infinite temperature. The color coding is the number of particles. So you see that here there are many particles. They live on the checkerboard. And here there are a few particles and they're just scattered around. So this is a gas and this is a solid. So these lattice models does something a little crazy. which is to go from a solid phase to from a gas phase to a solid phase as you heat it up. That's, of course, contrary to everything we see in nature. Okay, now let me explain why this is happening. This is a heavy slide. I'm gonna try to explain using mean field theory why this is happening. I'll then explain how this is consistent with the entropy being maximized, even though it's an ordered state. So we have to compare the free energy of the solid and the free energy of the gas. That's the logic of this argument. And so let me just go through it. You start from the solid phase and you try to estimate its free energy. If you assume that you're in a solid phase, then you can drop the repulsion term. So then the repulsion doesn't do anything because in the solid phase, there are no nearby occupied sites. So you just have to calculate the free energy from this term under the constraint that you're in a checkerboard pattern. And so the average number of particles on each of the checkerboard sites goes like linear in temperature because it doesn't see the other guys. And that just follows from dimensional analysis when you drop the interaction term. And by contrast, in the gas phase, the number of particles per site only goes like the quarter, the temperature to the power of a quarter, rather than linear in temperature. So what I'm saying is that in the gas phase, all the sites are occupied on average, but the number of particles per site goes like the quarter, the 1/4 power of the temperature. While in the checkerboard phase, only half of the sites are occupied, but the number of particles in each of them goes like the temperature. And that allows you to calculate the free energy of these two configurations by just taking each of these and just raising it to the power of the occupied sites. And you get the temperature to the power L²/2 in the solid versus temperature to the power L²/4 in the gas. And clearly this wins. So this wins as long as the power of the repulsion is above 1. That's why I said that we know what happens as long as this power is not 2, but anything above 1. But if this power is exactly 1, the gas and the solid are degenerate, and you need to do something much more sophisticated to understand what's going on. And we don't know the answer.
Quick
So we see
question,
that in this.
Zohar.
Oh yeah.
Did
Is it
people
me?
simulate the case of the power one?
Oh no. It's a new model. I was thinking to do some because you see the leading order in field theory gives the same answer.
Right.
It both gives they both give L²/2. So I was thinking the right way is to calculate the deviations from mean field theory
Right.
and see who wins. But even that turns out to be extremely complicated. You get some Toeplitz determinant, and I don't know if it's solvable.
But it should be trivial to simulate. This is what I'm saying.
Trivial to you, not to me.
Okay, but
Yes, but in principle, yes. We just wanted to try to do something analytic before we simulate it. If you're interested, just send me an email. We're just starting to think about it.
okay.
But every time I gave this talk, people ask me, what about the power one? What about the power one? Because they say the model is quadratic. It should be solvable when the power is 1. But it's kind of not the case because it's quadratic, yes, but the range of parameters is weird.
Right.
Yeah. Yeah. So here the solid dominates at high temperatures. And the main thing is that this means that there is spontaneous symmetry breaking at high temperatures. So this deviates from all the theorems, all the expectations, and the reason is why. So naively, of course, I have to explain to you how come the fact that we have a checkerboard order maximizes the entropy. This must maximize the entropy, even though it has a checkerboard order. So what's the point? I think the point is clear from the solution that I gave you in mean field theory, which is that yes, you sacrificed some entropy to have a checkerboard pattern. But that allowed you to put so many particles in each site that the fluctuations of the number of particles on each site gives you so much more entropy. So you sacrificed a little bit of entropy and got order, but that opened up a huge phase space of possibilities. So that's the intuition. So the mechanism is that sometimes ordering some subset of the degrees of freedom can open up many possible fluctuations for the other degrees of freedom. And it could actually be mathematically true that a typical high energy state is ordered. That's what happens in this model. A typical high energy state is a checkerboard. If you just count how many states there are at high energies, the vast majority of them is a checkerboard. So that's the main message. That's the main physical picture in the paper, that we show that this is possible, a possible mechanism to get order at high temperature. You just need to open up many possible fluctuations when you order some subset of degrees of freedom. And next, I'll show you that the same can be done in quantum field theory, a very standard quantum field theory, and you can achieve the same result essentially. But at this
Can I ask
point,
you a
you can kind
question?
of pick up. Yeah.
Sorry. So you say that this happens because we have infinitely many degrees of freedom, like n is a natural number, any natural number. If you change the support to rational numbers or say to real numbers, what changes? Like if we make it smaller or continuous?
Oh, no,
Uh,
I don't know about, I think real numbers doesn't matter. It would be the same.
and what
If n
about
was a
things
real
like
number,
rational
it would be.
numbers?
Hmm?
What about things like rational number? If we make this support to be smaller, sorry, larger.
If n, let's say, could be just 0, 1, or 2, let's say just 0, 1, and 2,
Okay.
then you would not get a checkerboard. Why? Because then it would be in this book. It would obey the assumptions of this book.
Hmm.
Because there is a unit distribution and the space of states is a direct product. So if n was just bounded by 2, it could be just 0, 1, 2, then no checkerboard. You'll just get a lattice gas.
Okay. So if it's not
If
bounded, it will always give the checkerboard.
it gives you checkerboard for this model, not
Okay.
for, it's important that n ranges from 0 to infinity, like the number of bosons per plaquette could be anything. If you limit it by some number capital M, you would get maybe some intermediate solid phase, I don't know. But you won't get a solid phase at very high
Okay,
temperatures.
okay,
You'll
I
get a
see. So
gas.
you interpret this as the
So
boson number. Okay, okay. You cannot
yeah, so
make it rational.
the reason that the entropy that you lose from the checkerboard can be compensated by something is because the number of fluctuations in the boson grows with temperature. And for that, you need
Okay,
an unbounded number of bosons at each plaquette. Okay?
okay.
Now, you can ask, is this model natural? I don't see why not. What's the problem? Like, there is no limit on the occupation number of photons, let's say. So
Mhm.
I think it's easy to cook up. If it was bounded, would it be useful? Still, yes, because if it's bounded by 2 million, then you'll have a very high temperature where you would keep the solid. So it's still useful even if it's bounded. I think it's a physical model. I don't see why not. Also, it can be simulated. It's not abstract. You can just solve it on a piece of paper for like 7 sites. Oh, probably not, but let's say for 2 by 2, you can solve it on a piece of paper. Yeah. Sorry, I can't hear.
But Tuan, I think your mic is problematic. Maybe you can fix it and later ask the question. You can continue.
Oh, okay. Okay. So this is the main physics idea. The rest of the talk, there is something in the chat. Okay. The rest is just showing you that the same can be done in quantum field theory. In the paper, we also show that a similar thing can be done for superfluidity, topological order, superconductivity even. So even for superconductivity, we can have infinite temperature superconductivity with some simple tricks like that. But here I don't have time to do all of that. I'll just do quantum field theory, a simple model in quantum field theory. So I'm probably gonna be a little bit more quick now. So the first half I did slowly. I'm gonna be more quick because I won't have time to explain everything. So I'm not going to try to discuss gauge theories or models that are relevant for the ADS-CFT correspondence. That's a very interesting open question. I'm just going to discuss scalar field theories with some arbitrary quartic interaction. And I'll discuss them in the epsilon expansion. And at the very end, I'll just touch on 2 + 1 dimensions, which is the physical case with integer dimensions. So there will be 10 slides now about quartic interaction models in the epsilon expansion. These are some vector models. And I'll also take the large N limit at some point, just to simplify the analysis. Okay. And the claim will be that in this class of models, there are unitary, local, perfectly good models, which break a symmetry at finite temperature, and furthermore, at high temperature. And furthermore, the claim will be that it's exactly the same mechanism as on the lattice. So there will be some fields that condense at high temperature, but the entropy that you lose is compensated by some other fields that can now fluctuate much more wildly. Okay? So it's the same thing, it's just a little bit more formalism. So the fixed points in the epsilon expansion at one loop are the special values of these quartic interactions, which obey this quadratic equation. You can just remove the epsilon and write it in natural way like that. So this is the whole space of fixed points in the epsilon expansion. It's any quartic interaction which obeys this weird quadratic equation for the coefficients lambda. Actually, nobody knows what's the space of solutions of this equation. They were classified up to rank 7, I think, up to when the number of fields is 7 or 8. Otherwise, we don't know what's the space of solutions. And then you can put these models at finite temperature and calculate the condensates. Or something a little bit simpler, you can calculate the thermal mass, the Debye scale, for various fields. And this is given by a matrix. So the point is that this is the thermal matrix, a matrix of masses at finite temperature. So the point is that once you're given an epsilon expansion fixed point, you can shove it into this equation and check if the mass matrix has negative eigenvalues. If the mass matrix has negative eigenvalues, that means that there is a condensation at finite high temperature, at arbitrary high temperature. Now, of course, this almost never happens. Otherwise, you would have heard about it. If you, for instance, this is the most famous fixed point. This is called the ON fixed point. It also has a very nice ADS-CFT dual, which is a Vassiliev theory. Well, very nice is probably a stretch, but it has a dual an ADS dual. And you shove it into these equations, you find, of course, a thermal mass which is perfectly positive, definite, with no negative eigenvalues, and that corresponds to the usual thermal gap in a magnet. So this fixed point is like a toy model for a magnet, and of course it loses magnetism at high temperatures. So the point of our work is that actually there are variants. We checked many examples, first of all. So there is the ON model, which is the simplest magnet, but then there are various anisotropic magnets that are called cubic, tetrahedral, bifundamental, Michel, MN, tetragonal. We checked all of them, and in all of them, there is no symmetry breaking at high temperatures. It's a rare phenomenon. But there is one example, which is called the biconical model. There is one perfectly fine unitary fixed point in the epsilon expansion for which there is a negative eigenvalue. It's the biconical magnet. It has two order parameters. This is the symmetry group. It's OM times ON minus M. And it has order parameter under the first OM and an order parameter under the second ON minus M. So phi1 is the order parameter of OM, and phi2 is the order parameter of ON minus M. And you just put in these interactions. And then you find the fixed points in the epsilon expansion. You get these quadratic equations. These are just the fixed point equations. That gives you the fixed points in the epsilon expansion. These are like some examples where 2m is n. You shove it in to the thermal mass and you find that there is a negative eigenvalue. Okay, it's not very deep, It's a true fact about the epsilon expansion that there are these funny magnets which break a symmetry at arbitrary high temperature. Now, I just wanted to say in 5 more minutes a few more words about these models. These models have very large.
Actually, you don't have to finish 5 minutes later. We don't have a time restriction unless you have a time restriction.
Say again,
I
please.
mean, we don't have a time restriction. You can go on.
Well, I have to finish by 10, so I was
Okay.
just planning to give you a flavor of what's being done in the ON models because the details are
Okay.
not important. And
Okay, it's up to
then,
you.
yeah, my plan is to get to 2 plus 1D, which is kind of a little bit more interesting, to go to epsilon equals 1. So far, I'm just going to give you a preview of what's happening in the epsilon expansion. The disquartic models have a biconical fixed point. This fixed point is called biconical, and it has a negative eigenvalue for the mass squared. Okay, and it breaks the symmetry at arbitrary high temperatures. The only thing I want to say about these epsilon expansion models, which is kind of maybe interesting, is that there is a very natural large n limit for these biconical models, and there is a whole circle of fixed points. So one fixed point is, of course, just the usual critical ON model, but then there are new fixed points, and one of the fixed points here turns out to survive to finite n and to finite small epsilon on this side, and it's the one which breaks the symmetry at high temperatures. It's a multi-critical fixed point. It has 4 relevant operators. So it's very fine-tuned, but it exists. And so we calculated its phase diagram at finite temperature, and we proved that it breaks the symmetry at arbitrarily high temperatures. Now I'll show you what the bottom line is after a lot of analysis. So the bottom line is the following. This model, this is the symmetry of this model. This is where I'm going to slow down again because I'll get to some conceptual things. So these are epsilon expansion fixed points with this symmetry group, OM times ON minus M. And it turns out that at very high temperatures, it breaks the symmetry to this, OM minus 1 times ON minus M. So it just breaks one of the OM symmetries a little bit to OM minus 1, and you get continuous Goldstone bosons at arbitrary high temperatures, at least within the epsilon expansion. Now, how does it choose which of the two groups to break? It breaks the one with smaller rank. In the case of equal rank, you have to do separate analysis. It's more complicated. But if the two ranks are not the same, it breaks the one with smaller rank. And that's great. So these are existence proofs that this can happen in quantum field theory, at least within the epsilon expansion. But of course, we're not interested in quantum field theory in 3.99 dimensions. We're really interested in 2 plus 1 dimensions. We're also very interested in 3 plus 1 dimensions. But in 3 plus 1 dimensions, conformal field theories have gauge fields, and I have not analyzed what happens to theories with gauge fields. So with scalar fields, the interesting fixed points are in 2 plus 1 dimensions. So the question is, what of this is of any relevance to 2 plus 1 dimensions? An important theorem is that in 2 plus 1 dimensions at finite temperature, you cannot break continuously. You cannot break a continuous symmetry. Okay? So you might know that there is a theorem about 0 temperature, which is that in 0 temperature, you cannot break a continuous symmetry in 2 dimensions. A theorem, which is a small variant of it, is that at finite temperature, you cannot break a continuous symmetry. At finite temperature, you cannot break a continuous symmetry in 2 plus 1 dimensions. So therefore, these models are interesting maybe as a mathematical existence proof, but they're irrelevant in 2 plus 1 dimensions because they all break continuous symmetries. Most of them break continuous symmetries. So when you take into account non-perturbative effects for epsilon equals 1, they generate a small mass gap because these are like because the theory of the Goldstone boson is some sigma model on a sphere and it's gap. So there was a picture here. This is the theory of the effective field theory at finite temperature is a sigma model on a sphere, and it just non-perturbatively develops a scale, and the Goldstone bosons disappear. So our quest to find an example of entropic order in quantum field theory must continue because these examples are at finite, they're just valid at small non-zero epsilon. These are scalar field theories. And they're irrelevant in 2+1 dimensions because there is a non-perturbative effect that removes the symmetry breaking in 2+1 dimensions. So this is only true in this is true in 3.99 space-time dimensions, but not in 2+1 space-time dimensions. Is that clear? This is just a small conceptual point. I probably went over it a little quick, but I have no choice. It's a little non-trivial. I cannot explain it pedagogically like I did for the first part. Are there any questions about it? Of why we must continue to search? Why this is not satisfactory?
Hi,
Okay.
Zohar.
Hmm?
Hi, Zohar. Eliezer
Hi.
had a paper on gauge fields in 4D.
Okay.
At infinite n, I guess, in that
Oh,
paper.
hi. Yeah, so you can ask, what about 3+1 dimensions? And you need gauge fields to have non-trivial fixed points, but we don't have any example with finite n.
With
The
finite.
example that you brought up was an example of spontaneous symmetry breaking at high temperatures, but only in the planar limit. So if you took finite n but large n, it wouldn't work, that example.
Mm-hmm.
So it relied on a fixed point that doesn't exist at finite n. That fixed point is an artifact of infinite n.
Okay, I see. Thanks.
Yeah, so unfortunately in 3+1 dimensions, the field is, we don't know yet if there are examples. In 2+1, that's what I'm getting at. I showed you examples in the epsilon expansion, and I'm going to try to tell you something about 2+1 in the next 5 minutes. Are there any? So most important, is it clear why this is not satisfactory in 2+1 dimensions? It's because of a non-perturbative phenomenon that removes the symmetry breaking. Okay, so I continue. So there is one special, if you're very careful, you would have seen that there is one special case here that actually might work in 2+1 dimensions. That's the case of m equals 1, because in that case, the symmetry breaking is discrete. So there is one special biconical fixed point where one order parameter is just a scalar field which is real. So it's the symmetry is acting by plus minus. And maybe that biconical fixed point where one of the scalar fields is not a vector, just a real scalar field, maybe that works in 2+1 dimensions. It could. So the Lagrangian is the following. The Lagrangian is just, instead of phi1 vector, you just replace it by some phi1 squared, and it's a real scalar field. And then there is a vector phi2, which is an order parameter for ON, and some interaction. Now, it took us a lot of time to understand what eventually happens with this model. Because it's non-perturbative, it's strongly coupled, and we try to solve it by taking the large n limit in this group, but keeping this fixed, because you cannot touch it in 2+1 dimensions. And that took a lot of time. And so what happened was that in September, there was a numerical simulation of this. Well, there was a simulation of this model. It's not really a numerical simulation, but there was a simulation of this model. And they said that actually does break the Z2 at all temperatures. And we got excited again and started working on it, trying to prove it analytically. And surprisingly, we succeeded this time. And we now know that this model does break the Z2 at all temperatures. It's a variant of the biconical fixed points, and it has a Z2 order at all temperatures in 2+1 dimensions. So for what values of n? Okay. My calculations and Fyodor's calculations suggest that this works all the way down to n equals 4. The simulation in this paper suggests that perhaps n equals 10. So we know that for large enough but finite n, this model achieves order at arbitrarily high temperatures. Maybe starting from n equals 4, maybe starting from n equals 10, I don't know. But it works, and it's been proven. There is no contention about this model. It's now been completely proven that it works. So now we have examples on the lattice, examples in QFT, and the situation is pretty satisfactory. One thing is missing is what was remarked by Dean, which is that we don't know what's happening in 3+1 dimensions, and we don't have an example of continuous symmetry breaking at high temperatures in 3+1 dimensions. We don't know if that's possible. It's actually more interesting because the order of a continuous order parameter loses more entropy than a discrete order parameter. So it's actually interesting to see if such examples exist. Okay, so similar ideas can be done not just in QFT, for superconductivity, for superfluids, topological order, and so on and so forth. So now I have like 10 minutes for questions, if there are any. I'm happy to talk.
So actually, I have one.
Well, thank you.
In
Yes.
the very beginning, you talked about the lattice gas models. Actually, I consider what is the limitations of this theory. Can we recover any Hubbard model or any Landau-Ginzburg theory? Because there are 50 theories of superconductivity, as you said. Can we recover from this model?
Yeah. From which model? Though. Which model?
For example,
This one?
yeah. Just theories like this. Can we say that we can recover, for example, Ginzburg-Landau description of superconductivity and do all of things and again obtain a high temperature order in our cases?
Well, in our simulation, we studied what happens at this critical temperature here when the gas. So what is the order parameter? The order parameter is whether one sublattice is occupied or not. Okay, so the order parameter is the relative occupation of one sublattice to the other. So we actually found a sharp phase transition in this particular model at TC, and it's in the universality class of the Ising model. So you can say that the effective field theory near TC is the Ising model, some Landau-Ginzburg theory. It seems to be second order in this example. So yeah, the answer is yes. And also this example gives you a Landau-Ginzburg model at the critical temperature. So what's quirky about this example is that the high temperature phase is the ordered one. But the local description near TC is similar to the Ising model.
Actually, I've got a follow-up question about this, and actually you are partially answered. So we have, can we say that all of this theory is just lay in the universality class of the Ising CFDs and Ising theory, in essence?
Yeah, this is true, but it misses the point, no? Because for usual magnets, the ordered phase is here. And here we see that the ordered phase is here. So locally, yes, but the identification of what you mean by temperature is the opposite one from what you'd expect.
So actually, are there any breaking point why this temperature order switches? Are there any obvious reasons?
Well, yeah, that's what I explained here, that this model behaves differently from everything you've seen, perhaps, because the ordered phase has more entropy than the disordered phase. So I think, yeah, we just showed that high entropy does not mean disorder. It could be ordered. It could be the typical high energy states are actually ordered. That's the point of this model.
Okay, actually, I just wondered when you talk about this. Thank you.
Yeah. Any other questions?
So I also have a question. The Hamiltonian which you wrote in the back, I think. The important thing that was the n being large, right? The integer values n we can take. I mean, what happens?
Yeah, the important thing is that the integer values are unbounded.
Okay,
So
I
there is a finite but non-zero probability for the plaquette having an unbounded, like a large as you wish, large as you wish number of particles.
Okay, unbounded is the important thing. Okay, I see.
Unbounded is the crucial thing because otherwise I said there is a theorem that forbids order from forming.
Okay, thank you.
Mm-hmm.
Hi, Zohar. I have a quick question.
Mm.
Where did you dig out the n equal 4? I mean, you performed a large n analysis, right? So
Yeah.
why
Yeah.
4?
So here the mechanism is that ordering this degree of freedom opens up many possible fluctuations for the other degree of freedom. And you can compare the entropy of the ordered state and the disordered state.
Mhm.
And in the large n limit, the ordered state always wins. That's why this model like achieves this weird thing.
Right.
But you can just calculate what's the entropy of the ordered state and the disordered state and see and just extrapolate to small n and see when
Okay,
the other wins. And that happens at around n equals 4.
I see.
So the ordered state has more entropy because there is some number times n, and the disordered state has some similar thing, but it's multiplied by n minus 4, roughly speaking. So when you go to n equals 4, somehow they flip.
Mm.
Something like that. There is some n minus 4 that appears in the comparison. That's a large n calculation. You cannot trust it.
Right, right. I understand.
And they got something else. They got like that it's 10 maybe.
And in this lattice model, though, when they do well, you said they didn't do a simulation. What did you mean by that? They didn't do a lattice simulation. They did something else for this model?
Yeah. They took this Lagrangian, and what they did was a functional renormalization, which means, I think, is that you take some subset of the diagrams, you resum them exactly, and you drop some other set of diagrams.
Mm.
So it's kind of an exact solution, but only some subset of the Feynman diagrams. I think that's what people mean when they say exact renormalization group.
But I mean, is it trustable? This is something I don't. I mean, obviously, it works in this case, but it's
I
not
don't know
a
if it's
systematic
trustworthy.
approximation, or is there?
I
Is there
think I
some
heard that.
error?
Yeah, I heard that people at IHES nowadays are trying to see if there is a setup where this particular truncation is trustworthy.
Hmm.
But the general expectation is that it's not.
Okay, I see. And if one was to put this model on the lattice, then we would expect restoration on the lattice, would we? Or because generic expectation is that when you put a QFT on the lattice, is that again at high enough temperature you're gonna restore.
If the lattice has finitely many degrees of freedom per site, you mean?
That's right. So that's why I'm asking whether this one.
Well, you might expect if you put it on the lattice in such a way that there are finitely many degrees of freedom per site, then there will be eventual restoration.
Right.
But if the restoration is happening on the lattice scale, then it doesn't matter. Because if the restoration is taking place on the lattice scale, you would say that in the continuum limit, it's always ordered. Right?
But you gave,
Because you
I thought this was always true, but then you gave this interesting example that if you
No, it's not always true. In a typical lattice model, if you tune it to a critical point, the restoration happens at macroscopic temperatures, not at lattice scale temperatures. So our prediction here is that if you put this model on the lattice and you tune it to a critical point, the restoration will not happen at macroscopic temperatures, but on the lattice scale temperatures.
That I understand, yeah. But you'd still expect it if it's latticized that it does eventually restore at the lattice scale temperature.
Yes.
Yeah.
Yes.
There's no way around that. This is what I'm asking.
Well, it depends how you put it on the lattice, because you see, like, you could say that this model is that you put the Ising model on the lattice. Okay?
Yeah.
It depends how you put it on the lattice. And in this model, there is no eventual restoration.
Right.
So I don't know what you mean by putting on the lattice, because it's not like one procedure.
So you think that it may be possible to put it on the lattice in such a way that this property is preserved exactly for arbitrarily high temperature by violating?
It would be probably irresponsible of me to make a guess. I didn't try, I don't know. What we did is just in computations in infinite volume.
Right.
in the large N expansion.
I
And
mean,
these
I guess you
computations
could,
turned out to be brutally difficult. It took us more than 3 years to understand how to do them.
right? But in principle, the large N computations you perform could be performed on the lattice, presumably. I mean, more difficult, of course, because.
Yeah, I don't know. We didn't try. We didn't try.
Okay, thanks.
Okay. Any final
I think
comments?
there is no
Yes.
other question.
Let me see.
Actually, if there is
Okay.
a time limit, I can ask one more question, sir.
Sure.
Is it
I
okay?
can stay for another 2-3 minutes. Yeah.
So at the end of the presentation, I think there was topological order in the one of the examples. So how do we proceed in the topological order in this case?
Oh, I have a very simple answer to that. Take a look here. There is a whole section about it.
Oh, thank you. Okay. So
Yeah,
is
but
it
the idea is the
an
same. This paper has only one idea, and it's the same in all of them. You cook up an example where having some degrees of freedom order into topological order turns out to be beneficial entropically, and then you prove that at high temperature, a typical high energy state is topologically ordered.
Okay,
It's
thank
very
you.
different, of course, from topological order in real life. You know, like if it can be cooked up in real experiments, that would be like 17 revolutions one after another, because you could bring electricity from China for free with the high temperature superconductivity. You could stop worrying about decoherence in quantum computers because you could have high temperature topological order. So these examples are probably somewhat artificial, but they exist. They make sense, yeah?
Can I make a remark on that,
Sure.
Zohar? So
Yes.
if we do not consider thermal ensemble, but just consider insertion of some chemical potentials or ZQ grading,
Yes.
it is very easy to have ordered phases at arbitrarily small beta. You know, this is, for example, the idea of adiabatic continuity. But
Yeah, but
the
you need
notion
phases.
of
Phases.
the notion of entropy changes, however, yeah.
But Mithat, one remark. You would need really phases. I think chemical potentials don't do the job. You need phases.
What do you mean by I need phases? Exactly.
Well, I think you need to add to this ensemble. Do you see the slide or it stopped sharing?
Yeah, I see it. I see it.
You need to add something that has oscillating behavior.
Oh, yeah. That's the reason that standard entropy argument wouldn't work.
Yeah. So now the question is, how do you cook it in real life? In real life, nobody knows how to couple a system to an ensemble like that.
I agree. This thermal ensemble is the real life. Yeah, I agree with that. But
Yeah.
I'm asking a formal question. Why is it so easy to have, ordered phases when you put those phases there, while it is
Well,
so
nobody
difficult?
knows. First of all, you know, you worked out a lot of those examples, and we have some too, but I believe the answer must be that you're minimizing. I mean, here what you do, you say that at high temperatures you need high entropy, and high entropy is disordered. Well, of course, it's not true, but it's kind of true in many examples. I guess when you put phases,
Yeah,
it's just not true, but we
yeah.
don't really know.
We don't really know. Yeah, the notion of entropy changes. You have to think something like graded entropy or something like that, because there
Yeah.
is state cancellation.
Well, yeah,
Yeah, lots of states cancel. I don't know. I don't know why or how. But the problem is that putting phases in real life, I don't know how to do that.
Yeah, it's not. Yeah.
You can put the chemical potential in real life, but then
Yes.
everything like that still goes through. Once you put oscillations,
Yeah.
I just don't know how to do it.
I agree. Yeah.
So one challenge to you is to find how to realize coupling to a thermal bath with oscillations.
Yeah. Yeah.
I mean, one could imagine some kind of a non-unitary theory, right? With an imaginary piece of the Hamiltonian. Maybe some dissipative system has a weird
Oh yeah, yeah,
like
something
that.
like that.
Yeah,
Yeah,
maybe you can
sure.
model a dissipative system like that, and maybe that dissipative system.
Yeah. Yeah, there's some, this idea is called distillation of the Hilbert space, yeah?
Yes. Yes.
Yeah. Yeah, I don't know. So mathematicians don't prove anything about it. And like nothing is known about it in principle. We just have a few examples from your work and some others.
Mm-hmm. Mm-hmm.
But like concentrated just on this year.
Yes, yes. I
Okay.
mean, it's a very reasonable thing to do. It's very interesting, in my opinion, too. I was always assuming that if you go to high temperature, things will melt, kind of assumption. And you are
Well, it's
showing
not true.
counterexamples
Yeah,
to that. Yeah.
we have one very nice counterexample,
Okay.
which is very clear and you can simulate it and verify that it's true. So,
Hmm.
okay. Yeah, I'm happy to
Okay.
continue chatting about it just over email. I have to get going.
Okay, well, thank you so much for the
Okay.
talk, Zohar. It was very nice. It was a pleasure
Thank
to
you
have
so
you.
much for coming, and yeah, let's do it next time on a more happy occasion.
Yeah, sure. See you.
Yeah, we hope so.
Okay, bye-bye.
Bye.
Bye.